use substitution. That was a way of undoing the chain rule. When we do integration by parts, it's a way of undoing the product rule. So let me show you what I mean by that. Suppose I want to take the derivative of u times v. Well, product rule says that's the first times the derivative of the second plus the second times the derivative of the first. Now suppose I take the integral of all of this. The integral of a sum is the sum of the integral, so I can distribute this. So the integral of the derivative, they cancel out. I have u times v, and this becomes the integral of u dv plus the integral of v du. I'm going to solve for this. So the integral of u dv is equal to uv minus the integral of v du. And that's the formula we want to keep in mind. Now you may ask yourself, why on earth would I do this? Well, the hope is that this integral is easier to do than this one. So let me look at an example here. Suppose I want to integrate x natural log of x dx. We don't know how to integrate this. So I need to rewrite the integral. This mess here I need to rewrite as the integral of u dv. I need to pick some part that's the u and some parts that is the v. I'm going to let my u equal natural log of x, and I'll let my dv equal x dx. So now I've taken care of everything on that line. Now to rewrite it using my formula, I have to take the derivative of the u and integrate the v. So du becomes 1 over x dx. So I took the derivative here. I integrate this one. So that I get v equals, well, the integral of x is x squared over 2. So, let's I have no space. Let's use my formula. So the integral of u dv is equal to u times v. So where's u? U times v is the diagonal, so I have x squared over 2 times the natural log of x minus the integral of v du. Well, there's v and there's du. So I have x squared over 2 times 1 over x dx. And yes, if I simplify this, first let's rewrite all this crap. One of those x's will cancel, so this becomes x over 2 dx. That's just a constant. So that I can integrate. Have I gone off the page? Of course. Natural log of x minus x, the power rule for x says we've got x squared over 2. There's already 2 down there, so I'm going to get x squared over 4, and then we're not going to forget our plus c and lose a point. So the original integral was not doable the way it looked. But when we played around with it, massaged it, we got this one, which is an easy thing to integrate. That is the bottom line of integration by parts. It's you shaking this integral up using the formula. What do you choose to use u? Well, that takes time and practice, and we do have one mnemonic to help you. You choose u in order of preference, Liat. I should put this over here so it looks better. Liat. Oh, you can't see it. Your first choice. If there's a natural log or any kind of logarithm on that line, that's what you choose for your u. No matter what else is on the line. If there's no logarithm, you ask yourself, is there an inverse trig function? Oop, inverse, can't spell. Next, there's no inverse trig, there's no logarithm, then you look for an algebraic expression. It's like a polynomial. That's like the square root of x plus 5, you know, that sort of thing. This is an algebraic expression. Next, the T stands for trig, and the E stands for exponential. Exponential is your last choice. So is trig. They're both pretty bad. Think about it. When you integrate or take the derivative of these two guys, or take the derivative of u of an exponential, you're never getting rid of it. The derivative of e to the x is e to the x. The integral is e to the x, is e to the x. Trig, sine goes to cosine, cosine goes to sine. They just keep multiplying and getting bigger and bigger. Whereas if you take the derivative of an algebraic expression, it typically gets easier. Inverse trig, you just don't want to integrate that because we don't know how to integrate. Same thing with logarithm. So this is our choice for our u. And you need to just practice, and it makes it easier.